July 1944, near Saint-Lô. The morning air is heavy with the smell of damp earth and crushed vegetation. The German gun commander observes the scene through his heavy binoculars. The tank is completely immobile, bleeding fuel into the soil and beginning to burn. Stable concrete floors and specialized tools. Consequently, severely damaged German armor was routinely loaded onto flat cars and sent back to industrial rail hubs deep inside the Reich. A German tank needing an engine overhaul might be lost to the immediate campaign for months. The American Sherman, suffering the exact same level of damage, was towed to a field, gutted by a third echelon mobile crane, and fitted with a replacement engine within 48 hours. The echelon system ensured that a paralyzed vehicle never traveled further from the battle than absolutely necessary. It functioned like a massive, mechanical circulatory system, constantly cycling damaged armor just behind the lines and pushing it forward again. But this decentralized repair network had a voracious appetite. A mechanic with a chain hoist and a wrench is completely useless without a fresh transmission to drop into the empty hull. A system this fast required an endless, predictable supply of precise replacement parts. Delivering that hardware meant stretching a supply chain across 3,000 miles of contested ocean, a feat that demanded a completely different approach to how weapons were built in the first place. A wooden crate is pried open in a muddy French staging area. Inside, packed in heavy cosmoline grease, rests a tank transmission shipped straight from an assembly line in Detroit. An American mechanic hooks it to a hoist. The crew logs a confirmed, undeniable kill. They quickly limber their weapon and withdraw into the shadows before enemy artillery can blanket their position, lifts it into the air, and slowly lowers it into the gutted hull of a disabled Sherman. He does not need a metal file. He does not need a blowtorch to expand the steel. He does not need to re-drill a single mounting hole. He simply guides the unit onto the mounts and tightens the bolts. It fits perfectly. This seamless mechanical union was not a fortunate accident. It was the result of a ruthless, uncompromising philosophy of industrial standardization. To understand why the American repair system moved so fast, one must look at the completely opposite approach taken by the German armaments industry. The German military establishment treated tank design as an evolving art form. Their engineering culture prioritized continuous tactical improvement over mass production. If an engineer in a Stuttgart design bureau drafted a slightly better exhaust cover, a reinforced glacis plate, or a more efficient gear ratio, the factory often integrated that change into the production line immediately. This created a logistical nightmare. It meant that a Panther tank built in March was not identical to a Panther tank built in June. The supply chain was choked with a dizzying array of versions, subvariants, and field modifications. A replacement part arriving at a frontline German maintenance depot might be mathematically flawless. By all the established rules of armored warfare, that Sherman was a permanent grave. A tank with a shattered track, but it often failed to perfectly mate with the specific hull sitting in the mud. The German factories were staffed by master craftsmen who could machine a mismatched part to fit right on the factory floor. But a frontline mechanic, shivering under a tarp in the rain while artillery falls in the distance, does not have a heavy lathe or the time to custom fit a drive sprocket. The United States built weapons like they built tractors. The Ordnance Department enforced rigid interchangeability. The Sherman tank did have several distinct variants and utilized different engines to avoid bottlenecks in domestic production, but the fundamental mechanical interfaces were strictly controlled. The bolt patterns, the dimensions of the turret ring, the mounting brackets, and the track links were standardized across massive production blocks. A part stamped in a converted locomotive plant in Ohio would perfectly slot into a vehicle assembled in Michigan. This is why the German army could not simply copy the American echelon repair system. They possessed brilliant engineers and courageous mechanics, but their industrial base refused to freeze a design. They fought a war of artisans against an assembly line. The American repair network functioned at a blistering speed only because every single component in the supply chain was a known, predictable variable. The mechanics in the third echelon field shops did not have to fabricate solutions. They simply replaced modules. A pierced hull and a ruined engine is dead weight. Moving 30 tons of paralyzed metal across cratered, contested terrain requires immense pulling power, secure roads, and time. They stripped the broken machinery out, dropped the fresh machinery in, and sent the tank back to the fighting lines in a matter of hours. But even the greatest industrial supply chain on Earth was vulnerable to friction. Ports clog, cargo ships sink in the Atlantic, supply trucks run out of fuel or are blown apart by artillery before they reach the front. The predictable flow of boxed transmissions and crated engines from Detroit could, and frequently did, dry up. When the clean logistical network stalled, but the infantry still desperately demanded armor support for the next morning's offensive, the mechanics were forced to find another way. They had to look at the shattered, unsalvageable hulks waiting in the scrapyard, not as trash, but as a harvest. The rain falls steadily on a designated salvage depot in Normandy. It is a graveyard of ruined steel. One Sherman sits scorched, its turret warped by an internal ammunition fire. It is a catastrophic kill that will never fight again. But the ordnance mechanics approaching it in the mud are not there to document a casualty, they are there to harvest. The official supply convoy from the beachhead is stalled 20 miles back, choked by traffic and blown bridges. In the German doctrine of 1944, unless a crippled vehicle could be safely dragged back to a secure railhead, loaded onto a flat car, the combat battalion requires 3 operational tanks for the dawn offensive. Without fresh factory crates, the mechanics turned to the only remaining source of hardware, the dead. This was the Cannibalization doctrine. It was a grim, officially sanctioned reality of American armored warfare. When the clean logistical chain inevitably fractured under the friction of war, the echelon shops operated as localized battlefield assembly lines running in reverse. An unsalvageable tank was systematically stripped to the bone. If a Sherman was destroyed by a direct hit to the turret, its engine, transmission, and lower suspension were usually perfectly viable. If an anti-tank mine shattered the lower hull, the main gun, the periscopes, and the radio could be saved. Mechanics descended on the wrecks with heavy wrenches, crowbars, and acetylene cutting torches. They worked through the night under canvas tarps, severing undamaged track links, pulling intact carburetors, and ripping starters out of blackened engine compartments. A water pump, salvaged from a burned wreck at noon, could be bolted into a stalled tank by midnight. The German army also stripped their dead vehicles, but their lack of strict industrial standardization made it a gamble. A salvaged Panther gear assembly might not align perfectly with the next Panther hull without heavy machining. American standardization made cannibalization a mathematically certain enterprise. But this process was psychologically brutal. Extracting parts from a shattered machine or rebuilding a heavily damaged hull for a new crew and shipped to a heavy industrial depot, it was written off. The metal would simply rust in the Norman rain, often meant confronting the human cost of the armor war. A mobility kill usually meant the original crew escaped, but a catastrophic kill left a horrific interior. Ordnance mechanics were tasked with an unglamorous, dark duty. Before a repaired tank could be reissued, it had to be thoroughly sanitized. Soldiers used heavy fire hoses, stiff brushes, and buckets of water to wash blood, bone, and ash out of the cramped fighting compartments. They scrubbed the steel floors. They welded thick steel patches over the jagged armor penetrations. Finally, they applied fresh layers of olive drab paint to the interior walls to hide the scars of the previous occupants. When replacement crews arrived at the front, they were frequently handed the keys to these ghost tanks. A young commander might climb into his turret and smell the sharp scent of fresh paint, attempting to mask the faint, lingering odor of scorched metal. They knew exactly what the fresh weld marks on the armor meant. Yet, when the driver engaged the starter, the engine fired perfectly. The radio hummed with a clear signal. The tank was mechanically whole. By stripping one ruined machine, the mechanics could often return two crippled tanks to the fighting line. Through this relentless mechanical recycling, the combat strength of an American armored division was continuously resurrected from its own graveyard. The supply of parts never truly ran out as long as there were wrecks to strip. This grisly, invisible loop functioned in fields across the entire theater. The German crew knew that the numbers on their tactical map had permanently shifted in their favor, but the consequences of this hidden labor were about to bleed directly onto the operational map. When one side can rebuild its losses overnight in the mud, how does the opposing force even calculate if they are winning or losing? Inside a heavily camouflaged German command post, late in the summer of 1944, a staff officer leans over a situation map. The room smells of stale tobacco, damp concrete, and nervous sweat. The numbers tallied on his clipboard are precise and highly encouraging. According to the radio reports from the frontline anti-tank battalions, 42 American Shermans were knocked out in this specific sector over the past 3 days. Based on standard operational math, the American armored thrust must be exhausted. An entire combat battalion has been effectively erased from the map. The German commander orders his forces to hold the line, confident the enemy lacks the remaining armor to continue the offensive. The next morning, the horizon rumbles. The American armored column strikes the German defensive line with overwhelming force, appearing completely undiminished. The German staff officer assumes the Americans simply possess an infinite reserve of fresh tanks, driving straight off the landing beaches to replace the dead. This was a pervasive belief among the German high command, the myth of the endless American factory output. 4 days later, this same German unit holds a new defensive line 3 miles to the south. The optics are raised again, but the reality was far more complex and far more frustrating. The German frontline reports were not lies. The kills were tactically accurate. The anti-tank gunners genuinely hit the Shermans, the armor was pierced, the crews abandoned the vehicles, and the machines stopped moving. The fatal error lay in how German intelligence interpreted those reports. They measured a battlefield loss using their own rigid doctrine, where a paralyzed tank was a permanent subtraction. The German arithmetic was fundamentally broken because it treated an American tank like a German tank. Because the German command could not see the M32 recovery vehicles working in the dark, or the mobile third echelon machine shops operating under blackout tents, they existed under a catastrophic illusion. They believed they were fighting a war of permanent attrition. In reality, they were merely imposing temporary delays. Consider the true operational math. A single American armored division might suffer 100 tank casualties during a month of bitter fighting. To the German intelligence officer tracking the reports, that division is combat ineffective. It has been destroyed. But because of the relentless cycle of battlefield recovery, forward echelon repair, and raw cannibalization, 60 of those disabled tanks were pulled from the mud, repaired with standardized parts, and fed right back into the combat formations within a week. The division's actual combat readiness rarely dropped below 75%. Another American armored assault is rolling across the damp fields. The gunner locks onto the lead vehicle, watching the suspension cycle over the uneven ground. The German logistics system, however, functioned as a one-way street. A panzer division that suffered 30 tank casualties in the same month might only return 5 vehicles to the fighting line. The rest were either blown up in place because the specialized heavy tow tractors were unavailable, or they were loaded onto rail cars for a weeks-long journey back to an industrial depot inside the Reich. The German military was fighting an opponent that could recycle its dead on the battlefield, while their own losses were absolute. This created a devastating operational blind spot. German generals consistently believed they were winning the numerical exchange rate, only to find their defensive lines shattered by enemy units they had officially written off days earlier. They were being drowned by an invisible system they could not replicate. But the pressure of this logistical imbalance did not just guarantee American momentum. As the front lines shifted, the flawed German definition of a broken machine was about to become a fatal, self-inflicted wound. What happens when an army that relies on heavy factory-level repair is suddenly forced into a rapid, chaotic retreat? Late August 1944. A narrow tree-lined road in France is choked with retreating German columns. A 45-ton Panther tank violently shudders and grinds to a halt. But as the magnification clears, he sees something that defies the practical physics of the battlefield. The engine whines in protest before dying completely. There is no American tank in sight. There is no artillery barrage. The heavy machine has simply sheared teeth off its final drive gear, a common mechanical failure under the intense strain of continuous movement. The crew dismounts into the dusty road. Under normal circumstances, they would wait for heavy recovery tractors to haul the vehicle back to a secure railhead. But the circumstances are no longer normal. The front line is collapsing. The Panther was engineered for battlefield dominance, but its heavy interlocking road wheels and fragile transmission required meticulous maintenance in controlled environments. The entire German repair doctrine relied on a stable rear area and a static or advancing front line. It required time and secure infrastructure. As the German army was pushed backward toward its own borders, that infrastructure evaporated. The heavy 18-ton half-tracks required to pull the stranded Panther are miles away, either out of fuel or destroyed by Allied fighter bombers. The railheads that usually transported crippled armor back to the deep industrial depots have been captured or bombed into twisted iron. The logistics network has shattered. The German tank commander faces a bleak mathematical reality. Replacing a shattered final drive is a heavy, complex repair. Without a mobile gantry crane, secure ground, and the specialized parts that only a depot can provide, the Panther is paralyzed. A German anti-tank crew waits concealed within the thick ancient hedgerows of the Normandy bocage. The gunner leans into the sight of his 75mm PaK-40. There, on the side of the hull, is a distinct, freshly welded patch over a jagged gouge. It sits exactly where he placed his shot 96 hours ago. The American infantry is reported to be less than 5 miles away. The crew has only one viable option. They strip the radios, grab their personal weapons, and place demolition charges inside the fighting compartment. With a muffled detonation, internal fires consume the optics, the breech, and the engine. A lethal, perfectly armored weapon is reduced to a burned-out roadblock by its own operators due to a localized mechanical failure. This scene repeated itself hundreds of times across Europe. As the German army retreated, their rigid definition of a lost tank became a catastrophic, self-fulfilling prophecy. Minor breakdowns, thrown tracks, or simply running out of fuel transformed potent heavy armor into permanent, self-inflicted losses. Because the German system was not designed to fix complex machines quickly in the mud, A retreating panzer division left a trail of its own abandoned, self-destroyed armor in its wake. In many cases during the long withdrawal across France, more German tanks were destroyed by their own crews than by enemy anti-tank fire. The American repair system, by contrast, thrived on the advance. When the front lines moved forward, the battlefields full of disabled Shermans fell securely into American hands. The recovery vehicles and mobile machine shops simply drove forward, set up their blackout tents over the fresh wrecks, and began the harvest. The advancing army collected its dead and rebuilt them. The retreating army abandoned its slightly wounded and blew them up. The track is whole. The engine is running smoothly. The tank is advancing. This was not a hallucination, nor was it an isolated incident. The war of attrition was not won solely by thicker armor or larger guns. It was decided by the speed of the wrench, the availability of a tow cable, and a logistical doctrine that refused to accept a broken machine as a permanent loss. But when the fighting finally stopped and the massive industrial engines of both sides went quiet, what was the true legacy of this systemic disparity? The German gunner, hidden in the Normandy hedgerow, pulled the heavy firing lever and watched an American Sherman erupt into thick black smoke. He saw the crew bail out, recorded the shattered track, and confidently logged a confirmed kill. 4 days later, he looked through his heavy optics and saw the exact same tank, bearing the fresh weld marks of his own attack, rolling back into the fight. He believed the enemy possessed a miraculous, endless supply of fresh armor, driving straight from the landing beaches to replace the dead. He was wrong. The question at the heart of this battlefield mystery was never really about the thickness of the Sherman's armor or the lethal velocity of the German 75mm shell. It was about a much deeper, systemic truth. The German soldier thought he was fighting a localized duel against a single machine. Across the Western Front, German anti-tank crews, panzer commanders, and intelligence officers were recording accurate, tactically sound kills. He was actually fighting an invisible industrial system that stretched from the drafting tables in Detroit directly into the muddy pastures of France. He was fighting a doctrine that refused to let dead steel rest. The true, unglamorous weapon that guaranteed the Allied advance across Europe was not a heavy supertank. It was a recovery and repair network that treated a shattered vehicle as a floating inventory of spare parts. While the German military establishment built exquisite, bespoke masterpieces that required specialized gantry cranes and depot maintenance to repair, the United States built modular components designed to be swapped in the dirt. While the German army wrote off a mobility kill as a permanent grave, the American army treated it as a temporary logistical delay. The German command counted enemy losses. They could not count enemy resurrections. But this massive machinery of recovery was not an abstract force. An echelon manual cannot drag 30 tons of immobilized metal out of a flooded crater. Industrial standardization cannot patch a pierced hull. The system was entirely dependent on human labor, performed under some of the most miserable and terrifying conditions of the war. The brutal war of armored attrition was won by the driver of the M32 recovery vehicle, grinding his tracks, only to face the exact same vehicles days or even hours later. The arithmetic of attrition was failing them entirely. Through a contested field in the dead of night to hook a heavy steel tow cable under incoming mortar fire. It was won by the third echelon mechanic, shivering under a canvas blackout tent, using a chain hoist to drop a crated engine into a gutted hull just hours before a dawn assault. It was won by the welders, fusing thick plates over jagged armor penetrations, the supply clerks tracking wooden crates of carburetors across an ocean, and the exhausted ordnance crews who carried stiff brushes and buckets of water to silently wash the ashes of the previous occupants out of the fighting compartments. These unnamed laborers fought their war with heavy wrenches, acetylene torches, and crowbars. They scavenged the dead to resurrect the living. They ensured that every time a German anti-tank crew punched a hole in the American line, the steel would knit itself back together before the next sunrise. When the artillery finally stopped and the smoke cleared over Europe, the highways were littered with the rusted, blown-out husks of Panthers and Tigers, magnificent machines abandoned by their own crews for the lack of a tow cable or a replacement gear. They were fighting an enemy that seemed immune to permanent losses. The German gunner believed he had destroyed the vehicle. Past them rolled a ghost fleet of olive-drab armor. If you stood by the road and looked closely at the side of a surviving Sherman, you would rarely see pristine factory steel. You would see the raised, uneven scars of thick weld marks painted over and sent right back to the front line. You would see the quiet, undeniable legacy of the mechanics who refused to let the war outpace their wrenches. And by the rules he understood, he had. The armor was pierced, and the crew was forced to abandon it. But the fundamental disconnect lay in how the two opposing armies measured a shattered machine. To understand why this Sherman was rolling back into the gun sight, we first need to understand the vast, invisible machinery that activated the moment the original American crew ran for the trees. When a high-velocity shell shatters an engine block or severs a drive sprocket, the immediate physical result is always the same. The heavy machine stops. The turret loses power. The crew, if they survive the spalling metal, escapes, tracking a 30-ton olive-drab silhouette creeping across a narrow dirt road. The distance is exactly 400 meters. For the German army in the summer of 1944, this violent sequence almost always signified a permanent conclusion. Their belief was rooted in the harsh, practical realities of a military fighting a grinding defensive war, burdened by deteriorating supply lines and a chronic shortage of heavy transport. In the German classification system, if a panzer was immobilized in contested territory and could not be rapidly dragged away by its own retreating unit, it was lost. To pull a 45-ton Panther or a nearly 60-ton Tiger out of the mud required multiple specialized heavy half-tracks, which were always in short supply. If the recovery vehicles were unavailable, the crippled tank was either blown up by its own crew to prevent capture or left to rust. The German gunner in the hedgerow had not made an error in judgment. He had accurately applied the grim logistical logic of his own army to the enemy. But the United States Army did not measure combat losses using the same dictionary. They drew a sharp, highly structured line between two distinct battlefield events: a catastrophic kill and a mobility kill. A catastrophic kill was absolute. It happened when an ammunition stowage bin detonated, blowing the heavy steel turret completely off its ring, or when intense internal fires melted the hull into a warped, unsalvageable husk. He waits patiently for the vehicle to expose its broadside. The heavy firing lever is pulled. Those vehicles were genuinely dead. But anything short of that catastrophic threshold, a snapped track, a shattered transmission housing, a blown road wheel, or even a clean armor penetration through the fighting compartment, was not recorded as a permanent loss. It was viewed merely as a temporary change of ownership. The moment the surviving American crew abandoned their smoking Sherman and scrambled into the tree line, the tank ceased to belong to the combat battalion. It instantly became the operational property of the Ordnance Department. This bureaucratic shift was backed by a revolutionary logistical doctrine. The American military viewed the tank not as a single, sacred, indivisible weapon, but as a modular collection of standardized components bolted onto a steel tub. If a German shell ruined a main gun, the tank was not destroyed. It simply required a new barrel. If the engine caught fire, the armor, plating, and the transmission remained perfectly viable assets. The U.S. Army looked at a battlefield strewn with smoking, crippled armor, and did not see a graveyard of defeated machines. They saw a scattered, forward-deployed warehouse of valuable inventory waiting to be processed. This philosophy was invisible to the German frontline soldier. He could not comprehend it because it did not exist within his own formation. When a complex German tank suffered heavy battle damage, restoring it often required factory-level intervention or a long train ride back to the Reich. The muzzle blast flattens the tall grass, and a tungsten-cored armor-piercing round covers the distance in a fraction of a second. When an American tank was paralyzed, the factory came to the tank. To the German observer, the battlefield went silent after the artillery stopped firing. But for the American forces, the end of the shooting was merely the signal for a massive specialized operation to begin. Recognizing a damaged tank as a repairable asset is a useless theory if the machine remains in the kill zone. The physical reality required moving 30 tons of dead steel out of deep mud, often under the cover of darkness or enemy mortar fire. To understand how the Ordnance Department reclaimed these shattered hulks, we must look at the heavy machinery waiting just behind the front lines and the men trained to drag steel out of the fire. Night falls over the Normandy bocage. The infantry has dug in, and the artillery exchanges have settled into a sporadic, hollow rhythm. The battlefield belongs to the dead, the wounded, and the scavengers. Out of the darkness behind the American lines, a deep, heavy engine roars to life. A massive silhouette pushes through the brush. It shares the lower hull and tracks of a Sherman, but it lacks a rotating turret and a main gun. Instead, an 18-foot steel A-frame derrick rests, folded over its engine deck. This is the M32 tank recovery vehicle. It punches through the lower side hull of an American M4 Sherman, just above the rear bogie wheels. Inside its armored hull sits a winch capable of pulling 60,000 pounds of dead weight. The crew driving it are not frontline assault troops. They are ordnance mechanics, heavily armed and specifically trained to operate in the lethal, ambiguous space between the fighting lines. They approached the paralyzed Sherman disabled hours earlier by the German anti-tank crew. The abandoned tank is half sunk in the wet earth, its broken track a tangled mess of heavy steel links. To move it, the recovery crew cannot simply press a button. A mechanic must dismount in the dark, wade through a cratered field that might be laced with unexploded ordnance, and physically haul heavy steel towing cables through the mud. He must manually attach massive shackles to the tow lugs on the dead tank's hull, often while listening to the crack of distant rifle fire. It is exhausting, terrifying work. A single German flare popping overhead would freeze the mechanic in stark white light, exposing him and the recovery vehicle to waiting artillery. But the task is non-negotiable. The U.S. Army understood a fundamental law of physics that the German military apparatus often struggled with. Dragging a 30-ton machine out of a ditch requires a machine of equal mass and traction, preferably protected by heavy armor. The impact rings out like a massive steel hammer striking an anvil. Instantly, a violent gout of oily black smoke erupts from the rear engine compartment. By building the M32 recovery vehicle on the standard Sherman chassis and the earlier M31 on the older Lee chassis, the Americans ensured their tow trucks could go exactly where the combat tanks went. Furthermore, the recovery vehicles used the exact same engines, bogies, and road wheels as the casualties they were rescuing, vastly simplifying their own maintenance. The contrast on the other side of the line was stark. If a German Tiger or Panther tank broke down, towing it often required 2, sometimes 3, heavy 18-ton half-tracks, hitched together in a precarious chain. These half-tracks were unarmored, making daytime recovery under enemy fire virtually suicidal. Coordinating 3 separate drivers to pull in unison through deep mud, was a logistical nightmare. If the cables snapped or one half-track stalled, the heavy tank usually had to be abandoned and destroyed by its own crew. The American M32 simply rolled up, hooked on, and relied on brute force and armor plate. The heavy winch groans. The steel cables pull taut, singing under the immense tension, and the tracks of the M32 dig deep into the soil. With a violent shudder, the paralyzed Sherman is torn free from the earth. It is dragged backward, out of the crosshairs of the German guns, and towed a short distance behind the immediate front to a designated collection point. The mechanics have successfully stolen the machine back from the enemy. The right track snaps under the kinetic shock, unspooling into the mud like a broken watch spring. But dragging a shattered tank away from the fighting is merely the raw physical labor of the recovery system. Once the broken hull is hidden behind friendly lines, a much larger problem emerges. Pulling dead steel out of the mud is one thing, but rebuilding a ruined war machine in an open field, without the heavy cranes and specialized tools of a factory, requires a completely different kind of architecture. The heavy tow cables drop into the mud with a wet thud. The M32 recovery vehicle has dragged the pierced Sherman into a forward collection point, just outside the range of German light artillery. The air smells of scorched paint and leaking hydraulic fluid. An ordnance officer approaches the crippled machine with a clipboard and a piece of chalk. He inspects the shattered track, the torn drive sprocket, and the burned engine compartment. He is performing triage. The tank requires major surgery, but in the American system, it will not be sent back to a factory. The factory will come to the field. This was the echelon maintenance system. Instead of centralizing repair deep in the rear, the U.S. Army pushed heavy industrial capabilities as close to the front line as physics and enemy fire would allow. The doctrine was divided into highly disciplined, rigid tiers based entirely on the time and tools required for a job. The first echelon was the tank crew itself, responsible for tensioning tracks, tightening bolts, and checking fluid levels. The second echelon belonged to the combat battalion's mechanics. Hatches pop open violently. 3 surviving American crewmen scramble over the hot steel, drop into the ditch, and sprint toward the tree line. If a repair could be finished in a few hours using basic hand tools and small bolt-on spares, it never left the battalion's control. These men worked in the dirt under camouflage netting, rushing to swap out broken road wheels or replace severed track links before the next morning's attack. But a shattered transmission or a ruined engine block required heavy lifting. That triggered a handover to the third echelon, the Ordnance Medium Maintenance Company attached to the division. These units were entirely self-contained mobile machine shops. They operated out of heavy trucks packed with lathes, drill presses, and acetylene welding rigs. Using mobile cranes, they could pull a massive radial engine out of a Sherman hull in the middle of a French pasture, often working through the night inside light-proof blackout tents. If the damage was even more severe, the tank was passed to the fourth echelon, which consisted of heavy maintenance units established in captured barns or warehouses just a few dozen miles behind the fighting. The German military struggled to replicate this layered flexibility. While their frontline mechanics were highly skilled, the immense weight and intricate design of late-war tanks, like the Tiger and Panther, often defeated forward repair. Changing a Panther's transmission required tearing apart the driver's compartment and lifting the unit through the roof. Replacing a Tiger's inner road wheel meant removing multiple overlapping outer wheels in deep mud. These were complex tasks that demanded heavy gantry cranes,